Let z1 equal s plus 8i and z2 equal t plus 8i, where s is an element of R, t is an element of R, and I squared equals minus 1. Given that the modulus of z1 equals 10, find the possible values of s. So we want to get the modulus of z1. z1 is s plus 8i, and we know that that's equal to 10. Well, that's the square root of the real part squared plus the imaginary part squared. So we just square both sides of this and we get s squared plus 8 squared equals 100. S squared is 100 minus 64 is 36. The square root of 36 has two values, either plus 6 or minus 6. So that means we have two possible complex numbers z1. If s equals 6, we have z1 equals 6 plus 8i, here's z1. If s equals minus 6, we have z1 equals minus 6 plus 8i. And the moduli of these complex numbers should be 10. In other words, the distance of them to the origin is 10. So that makes sense actually. See, we have a right angle triangle here of sides 6 and 8, and another right angle triangle here of sides 6 and 8. So this point here is actually the image of this point under reflection or axial symmetry in the imaginary axis. It's like we're taking the point 6, 8, reflecting it through the y-axis and getting the point minus 6, 8. So only the x value changes sign. The y value stays the same. Given that the argument of z2 equals 3 pi over 4, find the value of t. So argument of z2 or arg of z2 is 3 pi over 4 in radians. We can convert that to degrees if you like. Pi radians is 180 degrees. So 3 pi over 4 radians is going to be 135 degrees. So the complex number must be in this quadrant here, because we want the angle from the positive real axis to this line to be 135 degrees. We measure anti-clockwise from the positive real axis, so the complex number must be in this quadrant. The complex number z2 is t plus 8i. So we have the imaginary part of this complex number. We see that it's 8. Of course, this 8 means 8i, dealing in units of I here on the imaginary axis. The real part of it is t, and we can see that t is some negative number. Well, if this angle is 135, it means that the angle in here must be 45 degrees. We can also see that for this right angle triangle, the tan of 45 degrees is the side opposite 45 degrees, which is 8 units long, divided by the side adjacent to 45 degrees, which we can say is t units long. So then, to get t, we just interchange tan 45 and t. So t is 8 divided by tan 45. The tan of 45 is 1, so we get 8 divided by 1, which is 8. So the length of the adjacent in this right angle triangle is 8 units. Here by t, I mean the magnitude of t, if you like. Just the length of the adjacent side to 45 degrees in this right angle triangle. But of course, the value of t, the t value itself is negative. It's minus 8, because complex number must be in this quadrant. So that tells us that z2 must equal minus 8 plus 8i. Use the Mouse Theorem to find in polar form the 5 roots of the equation z to the power of 5 equals 1. Now we can write z to the power of 5 equals 1 in the standard form of a polynomial that is put 0 on one side, and we see that it's a quintic polynomial. That is, the degree of the polynomial is 5. Now a general quintic polynomial would look like this: az to the 5 plus bz to the 4 plus cz to the 3 plus dz squared plus ez plus a constant term f equals 0. So a, b, c, d, e, and f are constant coefficients. They can be any complex numbers. The coefficients a, b, c, d, e, and f. Now, in a previous video, I mentioned a fundamental theorem of algebra, which states that any polynomial has at most n distinct roots, where n is the degree of the polynomial. So the degree of this polynomial is 5, so that means it has at most 5 distinct roots. Now we can rewrite our polynomial in the following way. We just put both sides to the power of 1/5. So we have z to the power of 5 to the power of 1/5, that's z to the power of 1. We're after z. So z equals 1 to the power of 1/5, or the 5th root of 1 if you like. Okay, this number here is the root. This number also tells us that there are at most 5 distinct values to the 5th root of 1. Now, we know straight away, of course, that one value for the 5th root of 1 is 1. But we know from the fundamental theorem of algebra that there are at most 5 distinct roots, so we need to get other values for 1 to the power of 1/5. Now, to get those other values, we write 1 in general polar form. 1 is a real number. It's also a complex number, because all real numbers, the set of real numbers is a subset of the set of complex numbers. So 1 appears just on the real axis. What do we need to write a complex number in polar form? Well, we need its distance to the origin. That's r. And it's very easy to see what r is here. We don't have to use Pythagoras here. We can see that r is equal to 1. The distance of plus 1 to the origin is 1. R is always a positive number, by the way. So for so suppose you had to get the modulus of -2. Well, the modulus of -2 would actually be plus 2. So r is always positive. And it's very easy to get here. It's also easy to get theta. Theta is measured anti-clockwise from the positive real axis to this line. But you can see that theta must equal 0, because this line here is lying along the positive real axis. Actually, if we were looking at, say, the complex number -1, theta would be 180 degrees. Just be careful there. If our complex number is a positive real number, then theta is 0. So now we can write 1 as r cos theta plus I sin theta, where r is 1 and theta is 0. So you've seen this before. This is just r cos theta plus I sin theta. And you can check that it works out. If we multiply 1 by the cos of 0, we get plus 1. If we multiply 1 by the sine of 0, we get 0. So we get plus 1 plus 0i, or just plus 1. Now we want to put 1 to the power of 1/5. So we put this here, this 1 to the power of 1/5, and this complex number to the power of 1/5. Now, what I've written down here is just polar form. To get general polar form, we have to add a multiple of 360 onto theta. So we get 1 to the power of 1/5, which is just 1, times the cos of 0 plus a multiple of 360. Of course, adding a multiple of 360 onto our angle theta does not change the value of the cos or sine functions. N is an integer. So it's an integer multiple of 360. So we're just cycling around and back to where we start, and so on. This one cycle is 360 degrees. We could take another cycle, so 2 cycles would be 720 degrees, and so on. Now we use the Mouse Theorem. We multiply the power by the argument. So we get cos of 0 plus 360n times 1/5. Well, that's just 360n divided by 5. So our argument becomes 72 times n. Now you will see that we get different values for different values of the integer n. So here I have written out the 5 values for 1 to the power of 1/5, or in other words, the 5 roots of the quintic polynomial. Actually, I've written out 6 of them, but at n equals 5, we get the same value as when n equals 0. When n equals 0, we get the cos of 0, which is 1, plus I times the sine of 0, which is 0. When n is 1, we get cos of 72 degrees plus I sine of 72 degrees. When n equals 2, we get the cos of 72 times 2, which is 144, plus I sine of 144. When n equals 3, the argument is 3 times 72, which is 216. For n equals 4, it's 4 times 72, which is 288. For n equals 5, we get 5 times 72, which is 360. So now we've just recovered situation when n is equal to 0, because the cos and sine of 360 are identical to the cos and sine of 0 when we plugged in 0 for n. So that means that if we were to calculate our value for n equals 6, we would just be adding 72 degrees onto 360 degrees, which is the same thing as adding 72 degrees onto 0 degrees. So for n equals 6, we get this here, the same as n equals 1. For n equals 7, we'll get the same value as we got for n equals 2, and so on. So we keep recycling these values over and over. We know that there are at most 5 distinct roots, and from n equals 0 to n equals 4, we have 5 distinct values. Okay, we have 5 distinct roots of the quintic polynomial set to the 5 equals 1. So we have 5 distinct values showing up here. So we know we can stop at n equals 4. So we don't need this one, of course. Here I've plotted the 5 values on an argand diagram. So here is 1, here is cos of 72 plus I sine of 72, and so on. The modulus of all of these complex numbers is the same. Actually, the modulus is 1. Distance to the origin for all of them is 1. Or it's supposed to be 1 if I drew it accurately. It should be clear that it's 1 because the general form is cos of 72n plus I times the sine of 72n. The general form of a complex number is r cos theta plus I sine theta. So r would be the number out here, and that number is 1. Also, if we just get the modulus of this thing, we just get the square of the real part plus the square of the imaginary part. But cos squared plus sine squared is always 1, no matter what the angle is. Our 5 solutions are the corners of a regular polygon. These angles here are the same. Each of these angles is 72 degrees. In part 2, we want to choose one of the roots, which we call w, where w is not equal to 1. We want to prove that w squared plus w cubed is real. So I can choose any of these. I'm going to choose this one here. So I'll call it w. So you can choose any of these roots except w equals 1, except this one. So how do we get w squared? Well, we just use the Mouse Theorem. We have to square this number, we just multiply the power 2 by the angle. Notice that we actually get one of the other roots. Similarly, we can get w cubed. We just put w to the power of 3, use the Mouse Theorem, multiply 3 by 72 to get 216. Now we have to prove that w squared plus w cubed is real, so we have to add w squared onto w cubed. Well, we just add the real parts, so we get cos of 144 plus cos of 216, and then we add the imaginary parts, so we get I times sine of 144 plus sine of 216. If we want to show that w squared plus w cubed is real, all we've got to do is show that the imaginary part is 0. So we just have to show that this part here is 0. So you can just go to your calculator and plug this in. So we get the sine of 144, add on the sine of 216, and we get 0. So now we see that w squared plus w cubed is cos of 144 plus cos of 216, and whatever that is, it's just a real number. The I part drops out. Now this is supposed to be true for any value of w that we take, not just this one here.